Hello everybody, my name is Samiha Fadloun. I am PhD student at LIM Laboratory in Montpellier, France. I work under the supervision of Pascal, Poncelet, Mathieu, Roche, Arnaud, Sallaberry, and also Julien Rabatel. First of all, I am so sorry for not being there with you, but I have some hardest. Without further delay, I will start the presentation. I will present to you a part of our research work in visualization. Our goal here is to remove the node overlapping from 1D graph layouts. I will try to synthesize the work and present it according to the following plan. I will start with the context, then problem statement, next our proposal with case studies and alternative techniques, and finally, conclusion and future work. Now I will present the context. Our context focuses on 1D graph layouts, not on 2D graph layouts. The nodes are positioned on the axis. In addition to the edges are drawn as curves above or below the axis. This visualization is known as arc diagrams. As you see here, a lot of visualization are presenting as arc diagrams or especially in 1D graph layouts. Now I will present the problem statement. I will present for you an example of philosophers represented by arc diagrams. As you see here, the nodes are represented the philosophers and the edges are represented the influencing between them. We observe here a node overlapping that makes the nodes hard to distinguish. So our goal is to remove the node overlapping and to preserve the initial configuration of nodes as much as possible. To deal with this problem, we make some definition. V represents the nodes, P denotes the initial layout, sigma represents the ordering function of initial layouts. The inverse of sigma represents a function that gives us the node in this order. And finally, S, a function representing the size of the nodes. Based on these definitions, we want to find a function f that removes the node overlapping and meets the four requirements defined below. So I will start with first requirement. First requirement is optimally using the length of the segment. As you see here in the final layout and in the initial layout, we use in the final layout all the length of the segment or the axis comparing with the initial layout here. Second requirement is to remove the node overlapping. As you see here, in initial layout we have node overlapping. So final layout should not have the node overlapping. Third requirement is preserving the initial order. So final layout should have the same order of the initial layout. For example, if we have the order of marks, and spear, final layout should have the same order, not the inverse order like spear and marks. The last requirement is preserving the relative distance between consecutive pairs of nodes. So we must preserve the relationship between distance in the initial layout. For example, here we have a big distance comparing with the other distances. So final layouts must have the same relationship of distance. So here, as you see here, we must have big distance comparing with the other distances. Now I will present for you our proposal. We propose a function f that meets the four above defined requirements. You could see the formal proof in this technical report below. Additionally, given an initial 1D embedding of a graph, an overlapping free layout using a function f can be computed in the big O of n log n being the size of the node sets. Now I will present for you our case studies. Our case studies start with the graph. Then we construct the matrix of similarity of this graph. Then we apply MDS or multidimensional scale to get the light in one dimension. And finally we apply our approach to get the final layout without node overlapping. So our first case study represents Les Misérables, a novel of Victor Hugo. Each node stands for one character of Victor Hugo novels, and each connects a pair of characters co-occurring in at least one chapter. The size of each node represents the chapter's number where the character is mentioned. As you see here, we have the initial layers obtaining by MDS or multidimensional scale, and after applying our algorithm, we have the final layers without node overlapping. For more details, I will explain node proximity using this subpart of the previous layout. Firstly, we observe that the final layers haven't the node overlapping, comparing with the initial layers. For example, this part contains a set of nodes. As you see here, we extracted them in the final light. And also, as you see here, we have the orange nodes positioned side by side because they are overlap in the same position in the initial light. Given a light of UVW with this distance D1 and D2, and having a final light with the same nodes UV and W and with new distance D1 and D2. As you observe here, D1 bigger than D2. So the final light also has the same relationship, D1 of the final light bigger than D2 of the final layout. So as a conclusion, we preserve a relationship between distance, or in other terms, the distance also remain identical of D1 on D2 and D1 of the final layout on D2 on the final layout. Now I will explain the distance perception using the same subpart of previous layout using in node proximity. Giving this layout of UVW with this distance D1 and D2 which are equal, and having the final layout with the same nodes UV and W and same relative distance D1 and D2. As you observe here, U bigger than V and V inside U. It seems like V closest to U than W, but we have the same distance between U and V. So we apply our algorithm with special requirements for, and we get this layout, and this layout explains very well the relationship between U, V and W. So we get homogeneous layout with similar distance between UV and VW. As a conclusion, requirements for hence seems to allow a quicker and more relevant understanding of the data, which can help identifying and understanding clusters. Second case study represented a Pacific Viz co-authorship network. The nodes represent authors who published on Pacific Viz during the 2008 and 2016 period and having at least 3 articles. The edge connects the authors that have published at least 1 paper together. The size of each node represents the number of papers that have been published in Pacific Viz by an author. In addition to, we associate area char for each node to represent the number of papers that have been published by this author per year between 2008 and 2016. So, as you see here, the initial layer has node overlapping and the final layer has not node overlapping. Additionally, we add area char for more details. So, for more details, I will explain this subpart of previous layouts. So, as you see here, you have subsets of authors interacting with each other in an interesting way. So, they are parts of distinguished small communities in the network. In addition to S1 and S2 have no direct connection, but all of them are connected to 1 or 2 authors in S2. As a conclusion, our algorithm preserves the relative distance given by MDS or multidimensional scale, so it preserves the community structures. And also, working with one-dimensional graph layouts gives us the ability of using the other dimension for other purpose. Now I will present the alternative techniques. So there are a lot of techniques to remove node overlapping, which are used on 2 dimensions, and we can apply them on 1 dimension. However, all these algorithms have the same complexity in 1 dimension or 2 dimensions, and we have the optimal complexity comparing with the other complexities. And also, we compare these algorithms with our requirements, and as you observe here, none of them preserves the requirements 1 and the requirements 4. Finally, I will present the conclusion and future work. So, as a conclusion, I start with a node overlapping problem in 1D graph layouts, especially in arc diagrams. Then I explain the 4 requirements to remove the node overlapping problem. Next, I present for you the algorithm proposed to remove the node overlapping, which has a big O, N, log, and time. Then I show for you the 2 case studies, Les Misérables and Pacific Viz co-authorship network. Finally, I compare with the different approaches for removing node overlaps. As future work, we want to extend our approach to 2D graph layouts. Thank you for your attention. If you have any questions, please email me in this address email. Thanks.